Hey Chris, how are you? Can you hear me okay?
Yes, sir, we can hear you.
Okay, cool. Sounds good. All right, we'll wait a couple of more minutes and then we'll start. Okay, let's get started. So, welcome everyone. Welcome to Machine Learning 101. Today we will be diving into basics of machine learning. This is an interactive session. Feel free to ask me questions anytime you have it. So, let's get going. All right. So machine learning makes the world go round. Everywhere you see around you, there is probably machine learning at play under the hood, right? And here are a few examples that I believe are how we use machine learning in our day-to-day lives. Number one is obviously spam filter. There is no one who doesn't appreciate Gmail spam filtering technique. The other application that we keep on using is Netflix. You're pretty happy when you get good recommendations out of Netflix. And I'm sure at this point in time, you can't live without ChatGPT. So these are some real world applications of machine learning. Can you think of any other applications of machine learning that are around you? Can anyone comment to that end? Okay, I'll give you a couple more examples, right? So in most of these diagnostic devices like X-ray, MRI, there is some sort of intelligence built into it that will give the operator an idea whether the image quality is good or not, or they probably need to take one more time, right? So there are those capabilities in medical domain. Everyone probably knows you might have got so many fraud calls from variety of actors, different actors, right? Not all of whom have good faith in their heart. So there is a lot of fraud detection and machine learning happening at your bank level or even at your telecom company level as well. So those are some other use cases of machine learning. Let's dive next into what are some sites where you can go and learn more about machine learning. So two of my favorite sites, or rather my go-to resources for learning about machine learning, is a site called Papers with Code. So when you go onto this site, you will find all the papers organized by task, by category, and it's pretty nice. They also have something called leaderboard, and leaderboard, what it will do is it will tell you for each of these given tasks what all models are out there. So for example, if you say semantic segmentation, if you click on it, you will probably find all the different machine learning models for semantic segmentation. The next go-to resource is Kaggle. If you haven't heard already, Kaggle is a pretty good and interesting site. There are a variety of machine learning competitions happening on this particular site. So there are few competitions that doesn't have any price associated with it, but you get to learn, and we'll learn from those examples today as well. So Kaggle and Papers with Code, must visit site. You should definitely go check it out. So if you consider machine learning, is it a black box? To a certain degree, yes, it is a black box. It has some well-defined inputs and a well-defined outputs. But what really lies is, how do you train or how do you create this black box? That's where all the magic lies. That's where all the success lies. So at a high level, you might also have a question in mind: how does machine learning fit with deep learning and AI in general? So as you can see from this particular Venn diagram, AI is like a all-encompassing superset of both machine learning and deep learning, and deep learning is a very specific subset of machine learning, right? So what it means is there are algorithms out there which can be classified as machine learning algorithms, but not necessarily deep learning algorithms. All right. Now, what are the three main components of any machine learning system? The three main components of any machine learning systems are inputs, outputs, and feature, right? If you go back a couple of slides, we see this, right? There is an input, there is an output. So then what exactly is a feature? Let's look at an example. So if you go to Wikipedia, this is the definition that we find of what a feature is in context of machine learning. Basically, it's a measurable property and characteristics of a data set. It can be numbers, strings, and graph. So yes, features are sort of an input, but more categorically, it is whole bunch of things. And what do they look like? Let's look at it one more time. So the inputs and the outputs can be categorized into two parts, the continuous and the discrete. So let's say price is continuous because it can be ranging from minus infinity to plus infinity. When we talk about discrete input and output values, these are generally buckets. So let's say in context of machine learning, for spam classification, a given message either spam or not spam, right? So those are those two discrete values that we have. Now, let's say your boss comes to you and he says that, you know what, we need to build a pricing model for a property or set of properties that I want to buy in Mumbai. So, can someone tell me what would be a good set of features or inputs to a machine learning model that we can, kind of give to the ML algorithm, and it will spit out a value or a range of value for that particular property? Can anyone guess? Anyone? Okay, let's pick. Chris, what do you feel? Take a random guess on what would be a good feature to feed to an algorithm that predicts your house prices. Give me your wild idea of the feature.
So I was thinking the area, the area, a lot of the prices can depend on the area in which the house is situated in.
Yeah, that is correct, right? So
So
zip code could be one of the features that can go into the machine learning model. Correct. Can you think of anything else, Chirag? Do you have any ideas on what are the features could be input to a regression model that will predict prices?
Square feet area of the house.
That is correct, right? So the area of the house, yes, that can be a feature. Couple of other features I can think of is when the construction was done. Secondly, we can also go dig up the different government agencies or code and figure out if there are any pending litigations. Because let's say in a given area, if there are two buildings, both equivalent in terms of the area, and they were constructed around the same time, a flat in a building that has no litigation will be of higher value than in building that has a litigation associated with it, right? So that could also be one of the features. Excellent, thank you. um, let's take one more example. So there is this interesting competition on Kaggle that has to do with uh, you know uh, Titanic machine learning for disaster, right? So basically what it really tries to do is, given your profile as a person, would you have survived Titanic crash or not, right? So it's basically trying to predict yes or no value, that would you have survived or would you have not, right? So the data set is interesting. They have collected list of all the passengers and the attributes for each of these passengers, and they also have some sort of a label associated with it, saying that okay, did they survive the Titanic machine learning crash or they did not, right? So what could be good features for a classification problem like this? Any guesses? Okay, I'll give you mine. Probably say gender, age, where they kind of board a Titanic from, when did they do the booking. I believe, again, when you're doing machine learning, the idea is not so much to, kind of focus too much on the output, but kind of the data itself, right? The attribute of the data, because there might be a hidden pattern in the data that we might have not been able to understand or are able to comprehend. Okay, so let's move on to the next thing. All right, so there are three main categories of machine learning based on whether the labels are available or not. It can be classified into supervised learning, unsupervised learning, and reinforcement learning. So let me go a couple of slides back and go back to a diagram of black box. Okay, now depending on the output value, we can classify machine learning algorithms into two categories. One is a classification and the other one is regression, right? So as I just in the discussion of features, we talked about the housing price prediction. That is actually a regression problem. And the Titanic classification problem, that's actually a classification problem, right? So similarly, let's say if I give you an image and then I ask you to annotate that, okay, does it have a B or does it have an ant, that would be a classification problem. So that's one dimension on how you can classify the algorithm. The other dimension on which you can do the classification of algorithms is basically, do you have this output label or not, right? Now, if you don't have an output label, what will really happen is you're talking about unsupervised machine learning. So as you can see out over here, the unsupervised machine learning, what it's trying to do in this particular scenario, there's a category of algorithms called clustering algorithms, wherein given a set of data points, it will try and yeah. Uh, Sorry about that. It seems that I might have got disconnected in the meeting. I think we are back. All right. Let's continue and let me share my screen as well. All right. Give me a second. We'll start. All right. So yeah. Am I audible again, folks?
Yes, yes,
Sure, you
yes.
know.
Okay, cool. Thank you. So yeah, we were talking about three different categories of machine learning based on the availability of the inputs and outputs. So in case of unsupervised learning, you can see out over here, what it's trying to do is it's trying to kind of group set of data points into,
Hello, sir. Sir,
yeah.
some people are waiting to join.
Okay, hold on just a second. Um, Open the queue. How do I admit all? I think they're already added out over here, right? Shilpa, do I need to admit anyone?
Yes, sir. Ravi is waiting to join.
I'm not seeing any request out over here.
I'll ask him to rejoin.
Okay, fine, fine, no problem. All right, so let's get back to the discussion. So if the output label is available, meaning the target that you're trying to learn, now the target could be multiple things. In case of housing price, it can be the value of the property, right? And in case of classification, it can be a yes or no, right? So is it a spam, is it not a spam? If that target label is available, then the algorithm is called supervised learning algorithm, because we have bunch of examples and then there is an output target variable associated with it. Now, given that in supervised learning algorithm we have the label and unsupervised learning algorithm we don't have the label, why do we need reinforcement learning? The answer is determinism, right? So let me give you an example. Uh, let's say you're trying to teach a machine learning model how to fly a helicopter. Now that's a difficult job to do, right? Namely, it doesn't know if how can you put something that is of higher dimensions into like two buckets, right? So it can't be a classification problem because the output values are multiple values, right? Or let's take for example driving a car. The output value in this particular scenario would be the angle of your steering wheel and probably the acceleration and the brakes, right? So there are three outputs. In this particular scenario, it doesn't really fit into regression, neither does it fit into the you know classification bucket. So in scenarios where you have you know unpredictability or uncertainty, it's better that we model our learning problem as a reinforcement learning problem. So be it learning to fly a drone, be it learning to drive like a car, or even for learning to trade stocks. Yes, there are certain scenarios or certain companies that use reinforcement learning to do trading. And the way it works is the output is not clearly defined, but you have the ability to gauge the decision of the output. So as you can see out over here, there will be a state associated with each of the inputs available to the agent, and the agent can take an action, and the environment lets it know that okay, is it a good action or is it a bad action. Now let me give you another example of reinforcement learning. Let's say you get a new puppy dog and you are now supposed to train that puppy dog, right? So what are the two rewards that you can really give? You can either give him or her a treat if they perform well, or you can give him some punishment if they do something wrong. So that's in a way or in a crux what reinforcement learning is. You're trying to teach an agent whether they have taken good decision or bad decisions directly based on the environment. It's very hard for us to kind of collect all the sample data. All right, on the other hand, let me give you a couple of examples. 5 to 6 years back, there was a project by Google Brain called Alpha Star, and it basically learned how to play the strategy game of StarCraft. In that particular scenario, even they use reinforcement learning. A few years before that, OpenAI was working on reinforcement learning for Dota. So if you're a Dota fan, uh, you might have heard about OpenAI agent, and what it did was it actually played against human competition at an international, championship. So that's those are two scenarios where the output is pretty complex, and it's very difficult to get the training sample for these kind of games, right? So in those particular scenarios, the reinforcement learning was used. Also, do you remember Lee Sedol? So Lee Sedol was another human level player for game called Go, and there was AI that was developed by Google, AlphaGo, which kind of defeated that particular player. Even in that particular scenario, they were using reinforcement learning. So those are few examples of reinforcement learning. So just to summarize, based on whether the output is uh, continuous or discrete, it can be classified as a regression or a classification problem. So let's say if the output is continuous, meaning value from negative infinity to positive infinity, then it's a continuous output value, and then it's a regression problem. But if you have to choose for one of the buckets, then it's a classification problem and the output is called discrete. Based on the availability of the output target variable, we can define the categories of machine learning algorithms into three parts. You have your supervised learning, you have your unsupervised learning, and you have your reinforcement learning. So supervised learning is when you have the target value. If you don't have a target value, you have unsupervised learning. And if the environment or your actions is complicated and you cannot get like a lot of samples, in that particular scenario, use reinforcement learning. So these are like three categories of machine learning. Let's go a step ahead. Now let's take a step back and ask ourselves which of these particular tasks fall into which category of algorithm, right? So I'll start with few, and then I'll give you a rundown of it, right? So the credit card fraud is interesting because it can be modeled both as a regression problem and a classification problem. If you classify the output of a credit card fraud as either fraud or not fraud, then it's a classification problem. But let's say rather than just directly classifying the particular credit card activity as fraudulent, what you try to do is you try to create a score. Let's say you create a score from 1 to 10 on how suspicious a given transaction is, then it becomes like a regression problem. Now, credit worthiness, most of us might have thought about taking loan or already have loans. In this particular scenario, you have to go through the CIBIL process and get your CIBIL score. CIBIL score is nothing but credit worthiness score, and it's a regression problem. What it does is it takes whole bunch of input from variety of financial institutes as well as government institute and the other demographic data that they have collected over a period of time, and based on that they create how much civil score should be allocated to you. That's a regression problem. The autonomous driving problem, as I mentioned, because of the state complexity and things being deterministic or not deterministic, it can be classified as some sort of a reinforcement learning problem. For recommendations, what would you guess it would be? Anyone willing to comment?
Classification.
Anyone? Any guesses? Right. Let's see. Do we have some messages? Okay. Prasad says classification. Prasad, you're correct, but there are also certain set of algorithms that treat uh, recommendation problem as a regression problem. Let me give you an idea. Let's say you have two set of movies or two set of users. You probably want some sort of rating between 0 and 1, 0 being that they are totally dissimilar, and 1 being they are highly similar. So in this case you can also model recommendation engine problem as a similarity computation problem, and that can be treated as a regression problem. Okay. Now there is something called a big five analysis. So this is like a classical theory in psychology. What you try and do is you try to predict the five attributes of everyone's personality, and based on that you come to know what kind of personality a given person is. In this particular scenario, it's actually a mixture of both classification and regression. Why is it so? Because you're trying to predict the values for each of these five attributes, but they are like five discrete values, right? So this particular problem is a combination of both classification as well as a regression problem. Object detection, let's say you take a photo, you want to figure out what kind of glasses someone is wearing, right? Is it an aviator, is it a bomber, or a whole bunch of other kinds of glasses, right? In that particular scenario, it's the object detection. Now authorship attribution is pretty interesting. What most of these government agencies would probably do is what most of these agencies would do is basically they keep on getting threat mails or threat communication all the time. What they try and do is, based on the message, they try and predict the profile of the person. So there was this interesting competition. You are given like a whole bunch of text of say 100 different authors, and then you had to identify which author could have written that particular text, right? So in this particular scenario, it can be treated as a classification problem. Same thing with plagiarism detection. Plagiarism detection is nothing but, have you copied your entire essay from the internet? That I believe can be modeled both as a regression as well as a classification problem. Amazon reviews, you might have seen that people write, at times they write sarcastically like, "Oh, it was so good that I'm not going to buy again," right? So that is sarcasm at play. This again can be treated as both classification as well as a regression problem. Now, the last example is stock prediction. So there is a subcategory of all of these three buckets that I've talked about. But at times there is something also called as a time series prediction. It is kind of a regression problem. Do check it out, right? And there are a lot of real world applications of the time series analysis. One is power consumption. Let's say you're in charge of connecting all the different power grids across the India. How would you predict that how much power generation needs to be done in like next 1 hour, right? So those kind of problems is falling into something called time series forecasting or time series prediction. That is a specialized category of a regression problem. All right, let's move on to the next thing. Now we talked about three key components of a machine learning algorithm, right? Specifically, you have your inputs, you have your outputs, and in between sits the machine learning algorithm. So in context of, so the data set you're looking at right now is that from the Titanic problem that I just said. So if you look at the columns, you have your passenger ID, you have the target variable, whether they survived or not, and then you have your whole bunch of features, right? You have their name, you have their gender, you have their age, and whole bunch of other attributes, correct? Now this is basically features. Even though you have a categorical variable out over here. Now discrete variable and categorical variable are one and the same because they fall into buckets, right? So gender out over here kind of falls into male and female. In this particular scenario, what you really need to do is you need to do some data pre-processing. Remember again one thing, the input to most of the machine learning model is a number. So what you then do is you encode this information into a number. So what you do is go through the data set, wherever there is male you put in a 0, and wherever there is female you put in 1. So that way when the machine learning does its whole thing, it knows exactly what to look at and how to interpret it. Similarly, in case of ChatGPT and other text-based classification, what you're really doing as an input is you're just passing it as an array of numbers. So imagine you having a document with words, 5 words, what you would do is you would create the word to number mapping, and then you treat your document as a collection of numbers. We will get more in depth with this with a practical example in a future session, but right now in this particular session we just want to keep it very basic and keep it at very introductory level. So just to reiterate, this things that I highlighted out over here, which is input features, this can be both discrete as well as continuous. But because the way machine learning algorithms work, you need to convert your categorical variables into some sort of a numerical encoding. So at the end of the day, all of your text and strings, they also get converted into numbers. The next component is the target variable. What are you really trying to learn, right? So I believe 0 in this particular scenario means deceased and 1 means that they have survived. So that's the target variable, which is the second component of our ML model. Now, the third part is obviously the black box in between, which is the algorithm itself that does the machine learning, right? So there is this nice diagram from Java Point, and they have categorized the ML algorithms into different categories based on the classification criteria that I just talked about, few minutes back. So for supervised learning, we have our regression, we have our decision trees, we have our random forest, and we have our classification. Let me take a step back and talk about decision trees. Decision trees, what you do is you're given a table and you're trying to predict the target variable, right? So in this particular scenario, rather than doing like a classification tree, or coming with a classification value saying that did they survive or not, what you're trying to do is, okay, what group of people survived and what groups of people kind of didn't survive, right? So what it will do is, depending on the values of each of these input features, it will try to construct the leaf node, and the value of the leaf node would be the target value out over here. So that's a decision tree. And when you have a collection of decision trees that you're kind of inducing all together and then kind of aggregating their results together, that's where the random forest algorithm comes into play. Couple of unsupervised algorithms that I want to talk about is SVD. SVD stands for singular value decomposition, and PCA. PCA stands for principal component analysis. These are unsupervised learning techniques. What they do is they do a pretty bang up job of kind of creating a data representation of your features that it might not make sense to human, but it definitely makes more sense to machines, and then they use to kind of build better decisions out of it, right? K-means is a clustering problem. So clustering problem is very simple. As you can see out over here, you're given a whole bunch of data points and you're trying to kind of figure out which categories each of these particular data points lead into. Now, what's a real world scenario out over here? Let's say if you're responsible for a marketing budget of about 1 crore, you definitely want to know who your target audience is, right? So clustering will allow you to identify based on the customer database who my core target audience is, and can I group them into different buckets, right? That's where the clustering algorithm comes into play. uh, I want to talk about a priori algorithm as well. So turns out Walmart, when they started doing data science and machine learning, they found some pretty interesting thing. And the story goes as such is, what they found is, in most of their stores, whenever the diaper sales went high, the beer sales also kind of went high. They are wondering what exactly is happening. So as it turns out, whenever you become like a new parent in United States, you go to a diaper run. Basically, your wife will tell you to go fetch diapers. Interestingly, on the checkout aisle, there were also beer on display. So idea is, the tired father, whenever he goes to kind of get the diaper, he would also probably get beer as well, right? So how did they find this? They found it using the a priori algorithm. What a priori algorithm will do is, it will take all the receipts of all the transactions across Walmart, across all the store, and it will find that, okay, whenever people bought item A, they also possibly bought item B and C, right? Whenever they bought item E, they probably bought the item G and H, right? So that's a another name for a priori algorithm is market basket analysis. That's another name for this particular algorithm. All right. Now we probably have touched upon this point. What is the difference between supervised and unsupervised learning? What I did was I asked Google's Gemini to kind of come up with this, and this is what exactly it came up with. Right? It came up with a nice kind of bucketing or grouping of all the different things that you can do with regards to the machine learning part. All right. Now, dimensionality reductions, I talked about SVD and PC algorithms. This is useful, especially when you're dealing with images, when you're dealing with, say, audio data, right? Now, why is it called high dimensional data? Bear in mind, each pixel of your image has three values, RGB values, and that one pixel value is kind of is aggregate of these RGB values, right? So now imagine that if you have a pixel image of say 100 by 100, what you actually have is 100 by 100 into 3, and the 3 is the number of channels that you have for each of these colors, right? So just imagine, for a machine learning algorithm it might get overwhelmed because of lot of high dimensional data. And similarly with audio, right? If you look at audio, you can represent it as like a two-dimensional graph of time and intensity, but there are some other interesting representations of audio data as well, right? So there is something called fast Fourier transform. What that will do is it will convert your time domain signal into frequency domain, right? So rather than looking at the intensity versus time, what you're really doing is you're looking at frequency versus time. So those who play music might know what I'm talking about. First, for everyone else, you just have to assume I'm saying everything correct. All right. Now, uh, not everything is fine and dandy when you're doing machine learning. You have to be aware of these four horsemen, so to speak, of machine learning. So, what are these four horsemen of machine learning? One is overfitting, second is underfitting, third is data leakage, and fourth one is bias. Each of these are active areas of research, but let me just give you like a brief overview of what overfitting means. So, if you look at this particular graph out over here, we could have easily kind of trained this model by just assuming that the black line out over here is correct, which actually it is. But what our model kind of learned was this green line. It kind of complicated things than what it needed to. So what really happens with overfitting is that whenever you give it an input, it will kind of use its memory and not generalize well, right? So there's this important concept of generalization. So let me give you an example. When you're training your dog, it has been trained into your the home environment, but you want your dog to also behave well in, let's say, at your friend's environment. Well, that's kind of the analogy of overfitting. It kind of performs well within your house but not so much on your friend's house, right? So what it means is that if you give it a new instance which is similar to what has been trained before, it will not give you correct output, and that's where the overfitting comes into play, because it has so-called memorized things, right? You might have seen a lot of your friends, they memorize things and they got good marks, but when you ask like an applicative example of that particular thing, they might have failed miserably. Now, the counterpart of overfitting is underfitting. Underfitting happens when it will not utilize the complete data and it will not learn what is actually supposed to learn. Right? So those are the two concepts, overfitting and underfitting. The third messy thing that you have to deal when you're dealing with machine learning is called data leakage. Now, what data leakage simply means is that the machine learning model is cheating. How does it cheat? Well, it takes the sample of your output, or so again, there are two phases in machine learning. You have your training phase and then you have your testing phase. What really happens in your training phase is you're kind of teaching your model, and in testing phase, what you're really doing is you're checking that has the model learned enough or not. So what will happen out over here is that it will perform wonderfully well in training, but the moment it will go to testing, it will fail miserably. Why is that happening? Is because in your training data, you have a representative data from your test data, right? So ideally what you want to do is, even before you start your training and testing data, you want to kind of separate out the two. What you really want to do is, typical ratio is 70 to 80% of your data goes into training, and the remaining 30 to 20% goes into testing. Model evaluation is very important, because what will happen is, again, overfitting and underfitting are the real world examples of the problems that you can have once your model is kind of deployed into production. Now, the last bit I want to talk about is bias. Now, let me give you a very interesting example. You might have seen the viral video on internet where a person of a darker skin tried to use the automatic soap dispenser and it was not working for them. That is a classic example of bias, right? So let's say if you have your model that is not trained on diverse set of data and it's only kind of trained on one particular ethnicity, it might not work for the other ethnicity, right? It might not generalize well. So again, just to reiterate, the four horsemen of machine learning that we have to avoid are overfitting, underfitting, data leakage, and biases. Coming to the actual frameworks, these are the top three frameworks for machine learning. There are 10,000 more, especially in each of the programming language themselves. There is Wowpel, Wabbit, then there is Onyx, and whole bunch of other C, C++ tools out there. But these are the three popular ones. You have your scikit-learn, you have your TensorFlow, and you have your PyTorch. In the coming sessions, we will definitely touch on practical projects touching each of these frameworks, but understand that for now in machine learning these are like top three frameworks used for training your models or building like an ML model. Now I'm going to take some time and talk about some interesting models that I found on internet. The first one is Ultralytics YOLO. YOLO is pretty nice. You can do your object detection, you can do segmentation, classification, posing. OBB stands for boundary boxing. So you take your box and it kind of annotates those things. And the third one is track. The another interesting model is the aerial drone segmentation. What this particular model does is it has taken a whole bunch of images from drone camera, and then it has found like, okay, this is tree, this is car, this is house, those kind of things, right? It does like the semantic segmentation. By the way, Google Maps using machine learning as well, it takes whole bunch of satellite images and then kind of creates vector out of it, right? So when you kind of zoom in and zoom out, that's how it kind of finds all the polygons or different interesting areas in the satellite image. The other two interesting models that I found is Drone. What Drone does is, again, it's doing drone imagery, but from a different angle. And what it does, it tracks like, okay, is it a pedestrian? Is it like a lamp post? Is a car coming? Is a truck coming? That kind of classification. Insight Phase is another model that doesn't use deep learning. It uses the traditional machine learning. But what it will do is it will track your face. So it will identify the features. It will identify your nose, eyes, and lips, right? It will do that kind of identification. Lastly, a few takeaways I want you to take from this particular talk. There are two free resources that you can go check out. One is An Introduction to Statistical Learning. This is a very nice book, very well written. Yes, it has a little bit theoretical aspects to it, but it gives you a very good understanding of the mathematics behind machine learning. The other one is obviously by Ian Goodfellow and Yoshua Bengio. This is a deep learning book. This is like a bible of everything that I should do with deep learning. So yeah, that's it. I'm open up to any questions that you might have. Does anyone of you have any questions that I can answer for you? Okay, seems like no one has any questions. So thank you so much for joining in, and we will see you again in the next webinar. Thank you so much.